Equilibrium is a very familiar word and we use it in so many contexts. In physics, equilibrium implies a situation. We talk about the equilibrium of a body when there is no net force acting on the body. The body can have number of forces acting on it, but they act in such a way they cancel each other, and ultimately we get a situation where there is no net force on the body and we say the body is in equilibrium. Now, this equilibrium have got several characteristics, and actually we can have different types of equilibrium, and I would like to show that with a very simple experiment. For this experiment, I have taken this frying pan. If you really look at this frying pan, you will find that this blackened surface is a concave one and the other surface is a convex one. So, the two sides of the frying pan are having two types of surfaces, because this is not plane. This blackened surface is a concave surface and the bright surface is a convex surface. Now, see what we are really going to do with this. Now, I keep it like this, and let me take one ball, one of the metal balls. We can use a marble also. Now, when I keep it here, you can see this particular ball, we can say it is in equilibrium, no net force is acting, no net force is acting on it. Now, suppose we disturb it from its equilibrium position. What will happen? What do we expect to happen? By disturbing I mean I am really taking it away from the equilibrium position, and see what happens. The ball tries to move towards the equilibrium position, and in the process goes on oscillating about the equilibrium position. Let me repeat the entire exercise and have a look at it. It is in equilibrium position, and now I am taking it away from the equilibrium position and is releasing it. So, it goes on oscillating about the equilibrium position. This particular type of equilibrium is known as stable equilibrium. A body disturbed from its stable equilibrium position behaves in this way. We shall explain why. But before that, let us take a look at the other type of equilibrium. So, I make this pan upside down, I come on the outer surface, which is essentially a convex surface, and I once again try to keep the ball at the center. Now, you can see the body is once again in an equilibrium. Now, what do we really expect to happen if we disturb it from its equilibrium position? Let us see. If we take it away and keep it here, it really goes off. Here also it goes off. Here also it goes off. So, if it is really disturbed from this equilibrium position, we find it really goes away from the equilibrium position and does not come back towards the equilibrium position as we observed in the previous case. So, this equilibrium position is definitely different from the previous one. This equilibrium position is known as unstable equilibrium. So, in stable equilibrium we got a situation when the body in stable equilibrium disturbed from that position tries to come back towards the equilibrium position, and in the process oscillates about the equilibrium position. In fact, that happens with a simple pendulum also. And in unstable equilibrium, when disturbed from the unstable equilibrium position, it really moves away, it does not want to come back. Is there any other equilibrium position? Well, there is a third one. We call it neutral equilibrium position. Now, if you really keep the ball over here on this table, if you keep it over here, and this is also in equilibrium position, because there is no net force acting on the body, its weight is acting in the downward direction, and normal reaction is really keeping it at this position, which is normal reaction is equal and opposite to the weight. Now, if I really shift it over here from the equilibrium position, once again it remains there only. So, this is an equilibrium position which is different from the two previous ones. Here the body remains wherever it has been kept. If it is disturbed from that position, once again it occupies the new position and remains stationary. That means, it neither tries to come back to the old position like we observed in case of stable equilibrium, nor it tries to move away from the equilibrium position the way we observed it in case of unstable equilibrium. So, we can understand that even if there is no net force acting on the body, even if we have achieved an equilibrium, there can be different types of equilibrium, and we have to explain why it happens like this. For this, let us look at this diagram. For stable equilibrium, you can see this ball is really residing at the center of the concave surface when it has not been disturbed. In this equilibrium position, the forces acting on this body can be shown like this, and we can see why it is in equilibrium. Its weight W is acting in the downward direction, and the normal reaction N is acting in the upward direction. Since W is equal to N, the entire system is in equilibrium. Now, let us see why we call it stable equilibrium. Suppose we have disturbed it as we were doing earlier in the experiment, and we have taken it away from the equilibrium position, say towards our right. Now, what happens? The weight is still acting in the similar way. This is the weight, and in the normal reaction is different in the sense the normal reaction will act normal to the surface, and naturally this normal reaction is now not straight away not balancing the weight. In fact, this normal reaction has got two components, one in the vertical direction, another in the horizontal direction. Now, this component of the normal direction, that is normal reaction in the vertical direction, that balances the weight, and this horizontal component that tries to pull back the body towards the center. If we really move towards the left, same thing happens. That means, the weight is acting like this, the normal reaction is like this, and if we look at the two components, those come like this. Once again, the vertical component balances the weight, and the horizontal component pulls it back towards the equilibrium position. By the time the ball reaches the equilibrium position, because of this pull, it has already gained some kinetic energy. So, what happens? It really does not go and stop over there, it does not stop at the equilibrium position. It moves in the opposite direction. Once again, same thing happens, it acquires some potential energy, and then it comes back, it goes on and on. We can look at the situation both from energy point of view and force point of view. You will always find the ball is having a force in the horizontal direction that really brings it back to towards the equilibrium position whenever it moves from away from the equilibrium position. So, the entire thing is known as stable equilibrium position. Always the body tries to move towards the equilibrium position even if it is disturbed from that position. Now, we shall take at a look on the forces acting on the body when it is in unstable equilibrium, and why it is really unstable we shall be able to understand. You can see the ball is really residing over here. What happens when it is here? When it remains stationary at the top of the convex surface, the forces acting on the body were like this. You can see there were once again two forces, that is the weight of the ball W and the normal reaction, and at this topmost point these two are balanced, W is equal to N. Now, as we were doing, we were trying to take it away from the equilibrium position and we were trying to put it over there. If I really try to put the ball over here, what happens? Weight as usual acts in the vertically downward direction, but the normal reaction is once again normal to the surface. So, this is N, this is W. We can see that N does not balance W right away. So, there are two components of normal reaction, one in the vertical direction, another is the horizontal direction. Now, we can see that vertical component does balance W, but the horizontal component, what happens? It tries to take it away from the equilibrium position. So, once it has been put here, the ball has been put here, it has no scope of going back to the equilibrium position, rather it would move away from the equilibrium position. Same thing will happen if we really put it on this direction. The normal reaction is like this, and once again two components N1 and N2 will come, and the vertical component will balance the weight, while the horizontal component will take it away from the equilibrium position. So, this essentially tells us why in stable equilibrium the body, even if it is disturbed from the equilibrium position, taken away from the equilibrium position, because of the availability of a force, and we call this as restoring force, it comes back, it tries to come back to the equilibrium position. In fact, this essentially justifies the name restoring force. It restores its old and original position. On the other hand, if we look at the horizontal force in the second case, in the unstable equilibrium case, horizontal force is acting in such a way it tries to take it away from the equilibrium position. We call it destabilizing force, because it destabilizes the equilibrium. So, in both the cases, in stable equilibrium and unstable equilibrium, any deviation from the equilibrium position brings in a horizontal force. Of course, the vertical force is there that takes care of the weight. These horizontal forces directions are different. One is away from the equilibrium position in case of unstable equilibrium, and in case of stable equilibrium this force is towards the equilibrium position. So, the behavior of the body disturbed from these two types of equilibrium are different. Now, let us look at the third type of the equilibrium we have talked about. That is what we refer to as neutral equilibrium. By neutral equilibrium, as the very name suggests, that it is neutral in the sense it is neither stable nor unstable, so to speak. So, when the body is kept like this, you can see if we keep the ball over here, its weight is acting in the downward direction and its normal reaction in the upward direction. So, if we really try to draw the diagram of the forces acting on the body, it will be like this. When it is over here, W weight is acting in the downward direction, normal reaction is in this direction. Now, if we really shift it, as we were doing in the previous cases, to a different place, what will happen? The same two forces will be the players. There will be no other force coming. So, what happens? Wherever we keep it, there are only two forces, two equal and opposite forces that keeps the body in equilibrium. In this exercise, there is no emergence of any additional force, there is no emergence of restoring force, and there is neither emergence of destabilizing force. So, wherever you keep it, all the positions are equilibrium positions. So, this type of equilibrium is known as neutral equilibrium. These three types of equilibrium we come across when the forces are balanced on a body, or the body is under no net force, and depending on the situation we encounter in our daily life. I have talked about the oscillation of a pendulum. The pendulum bob remains in a stable equilibrium position. When you disturb it, it tries to move towards it. On the other hand, if you really keep a cone somehow with its tip in the downward direction, and if you just slightly disturb it, it will fall down. So, that is what is known as unstable equilibrium, and you will find more and more examples around you of both these types of equilibrium and of course, neutral equilibrium, if you take closer look at the situations around you. Thank you.